Okay, so there exists a unique Green's function. Okay, there exists a unique Green's functions. We did an example in this case. So what's the use of this is the next theorem. If G is the unique Green's function, then U equals to integral a to b G of t psi f psi t psi satisfies the equation Lu equals to f with b1u is 0 and b2u is 0. Okay, satisfies, or this is again the unique solution. Okay, satisfies or again unique solution of this equation. Moreover, u is unique. So uniqueness is not difficult to show. If there are u1 and u2 two functions, then you take u1 minus u2, and u1 minus u2 gives Lu equals to 0, and we are assuming that Lu equals to 0 with b1 u b2 equals to 0 has a trivial solution. Therefore u1 minus u2 is 0. Therefore u1 is identical equals to u2. Okay, so this we are assuming that there is a unique Green's function. Okay, so this equation. So what is L? L is Lu is we are taking p into u double prime plus q p prime u prime, right? P prime u prime plus q. Okay, this is what is our L. So what we do is we simply differentiate this. So we can write ut as integral 0 to j g of t psi into f of plus xi to you can take 0 to 1, so p g of t psi into f psi d psi. So differentiate this. So when I differentiate this u prime at t, sorry, this is 0 to t. So this is 0 to t. So there is a typo in the notes also. Okay, 0 to t and t to 1. Okay. So in this integral, the first integral we have the xi less than t. Okay, and the second integral xi greater than t. Right. So you write the u prime t. U prime t is going to be by the Newton-Leibniz formula. I can define, or you can write the fundamental theorem of integral calculus. So this becomes the integral 0 to t dou g by dou t, okay, to f of xi t xi plus you have the g of you have the xi is less than t, therefore xi minus comma t, sorry, xi, okay, f xi, and similarly this one will have t to 1, so dou g by dou t of into f psi t xi plus g of minus this time because t is on the lower side, okay, g of xi plus comma xi f psi. And we know that g is a continuous function. It is x t equals to xi. Therefore, these two, the sum of this minus this is going to be 0. Okay, so this is going to be 0 because g is continuous at t equals to xi. Therefore, you simply get the integral 0 to t dou g by dou t into f plus t to 1 dou g by dou t into f. So there is no other contribution other than taking the derivative inside the integral. So now let us do the second derivative. So u double prime. So let me write what is u prime first. You have the u prime t, which is which is 0 to t g of t xi f psi d psi plus the integral t to 1 g of t xi into f psi t xi to g by dot t. So now you write the second derivative. So the first term is going to be the taking the derivative inside, okay, and other one is coming from the Newton-Lagrange formula by differentiating the condition, that is the one of the boundary values, that is you are going to get tau g by dou t into xi minus gamma xi into f psi, okay, and this is going to be 0 to 1 tau square g by dou t square into f plus tau g by dou t into psi plus xi into f psi. The second one is with minus. So this is what we are assuming this as a gem. So this is going to be the first two terms, 0 to t of tau square g by dou t square into f plus t to 1 of tau square g by dou t square into f plus the gem, that is going to be 1 by p into f. Okay, so this is what we have. The jump condition, we assume that that is equals to f 1 by p. So now you apply the LU. LU is basically it's a linear operator. So L of u you apply, then you get 0 to t L of g plus t to 1 again L of g plus you have the L is basically L is p into u double prime. Okay, so when I take the u double prime, it comes and this is going to be p by p into f. So we know that this is 0 and this is also 0 because g satisfies both xi greater than t and xi less than t. It is actually L of g is 0. Therefore, this is equals to f. Okay, so you get Lu equals to f. And boundary conditions are satisfied by u itself, the g itself. G satisfies both the boundary conditions. Therefore, when I take u at the point A, it becomes directly, it goes on to the g because t variable is only in the g. And we know that g satisfies the boundary conditions. Therefore, u satisfies both the boundary conditions. Therefore, this becomes a solution of the non-homogeneous equation. So that's the advantage of writing the Green's function, is that you have an explicit formula. You have an explicit formula for the solution of a boundary value problem in terms of the Green's function. Again, the equations with constant coefficients are easy to solve using the Green's functions, but the existence of Green's function gives a lot of information, or it doesn't assume anything about the existence of explicitly what is the existence of a solution. Okay, so we don't require explicit solution. If you just know what is the Green's function, then we can write what the explicit solution is. Okay. So the second thing what I said is if you see what is the thing here, all throughout we assume that homogeneous equation has a trivial solution. So what happens if it doesn't have a trivial solution? I already said earlier what happens if it doesn't have a trivial solution. So if u naught is non-trivial solution, of Lu equals to 0 with b1u is 0 and b2u is 0. Okay, then the non-homogeneous equation Lu equals to f with b1u is 0 and b2u is 0 has a solution if and only if integral of f into u naught is 0. Okay, for all, yeah, so f into u naught is 0. Yeah, if for any u naught is a solution, then this condition has to be true. So this is same as what we saw in case of matrices. That's what I said in case of matrices. So if you take Ax equals to b, okay, and if A is non-singular matrix, sorry, if it is a singular matrix. Okay, so if it is non-singular matrix, then you have unique solution. That's what we saw in the previously. Non-singular matrix means that Ax equals to B, Ax equals to 0 has only trivial solution. That's the meaning of non-singular. Okay, so Ax equals to 0 has trivial solution if and only if A is non-singular. That's what we saw in the previous theorem. Now, if A is singular, okay, then this problem will have Ax equals to B has solution if and only if B x naught is 0 for all solutions of this Ax naught is 0. So this is what happens in case of matrices. So this is a theorem which is in the same spirit. So this equation Lu equals to 0 is the homogeneous equation. Here you have the homogeneous system. So the homogeneous system is same as the homogeneous equation. So if the homogeneous equation has a trivial solution only, means that it is a non-singular phenomena. If it has U0 is a solution for this, means that it is a singular phenomena, a non-trivial solution. So in case of that, you expect this kind of a orthogonality condition, which is also holds in case of matrices. The spirit is the same. Okay, so I gave the complete proof in the lecture notes. I'm not going to give here. You can interested students can read the proof. Okay, I'll just tell you why this condition holds one side. That is easy. So if U0 is a solution, okay, then you can write F into U0, which is F is nothing but Lu into U0. So this is since it is a self-adjoint equation, you can write this as like this, integration by parts. Okay, and Lu0, you know that Lu0 is 0 because U0 is a solution of non-trivial homogeneous equation. So one side you get like this, and the second side it's not difficult. You just write the general solution using the variation of parameters formula, and then substitute the conditions. Then you actually get a general solution. Okay, in the form of a very nice form, which is in the form of u equals to integral of the Green's function type of function times some arbitrary constant times this U0. Okay. So in the other side, you can show that one can show using variation of parameters formula. So you can write actually the solution in the form of 1 upon p times the Wronskian, okay, a to t u0 psi into a function vt minus p psi. I'll tell you what this v is. Not t, okay, into f of z is I plus c0, an arbitrary constant times u0. Okay, c0 is arbitrary. So that's what actually gives the infinitely many solutions, where v is a function where Lv equals to 0 with the conditions that b1v is not equals to 0 and b2v is not equals to 0. So Lv equals to 0 is, since it is a second order equation, you have a 2-parameter family of solutions. So from that parameter family of solutions, pick one function which doesn't satisfy these two. Okay, pick one function which doesn't satisfy these two. So that is with that, and v is another solution which satisfies these two boundary conditions. Therefore, u and v will be linearly independent. Once if you have two linearly independent solutions of homogeneous equation, you can actually write the solution of non-homogeneous equation using variation of parameters formula. So you write the general solution of non-homogeneous equation using variation of parameters formula, and then substitute the boundary conditions. So when you substitute the boundary conditions, you just have to use that the integral of f into u0 is 0. So that will give a general solution in this form. So the details are given in the notes. You can see that. Okay, so this gives infinitely many solutions. This is what we see in case of matrix systems also, that if you have a singular matrix, then the solution exists, and there are infinitely many solutions, or there are no solutions. If there is a solution, infinitely many solutions. It's precisely the case. Solution exists if and only if that orthogonality condition is true, and all the solutions can be written in the form of in this form where C naught is an arbitrary constant. So that gives infinitely many solutions. So I will stop this boundary value problems here. I am left with one topic, which is a small topic, which may be useful for you for writing several of these competitive exams later. So I just want to give an idea of this topic. If you have any questions, you can ask me now. And today and tomorrow I will teach that Laplace transforms. Okay. I have no questions, so let me continue with the Laplace transforms. So these are the problem solving kind of things. They are very easy. So what is the Laplace transform? So if I have a function f which is defined on the positive real line, okay, any function, then we define the Laplace transform like this. Laplace transform like this. So L of f at the point S is going to be the integral 0 to infinity e power minus st ft dt. Okay, provided the integral exists. Provided the integral exists. So the question is, what are the... So before that, let's look at some examples. Okay. So the first example is constant. What is the Laplace transform of constant? Okay, so ft equals to 1, therefore L of 1, which is going to be 0 to infinity e power minus st to dt. So you can check that this is going to be 1 by s. So let me take another function, f equals to exponential of at for t greater than or equals to 0. Then the L of e power at, it is going to be a function of s. So this is going to be e power minus st a to dt. So you can integrate this, it's easy, and then you can see that this is the case if not otherwise. Therefore, Laplace transform of this function exists for all s greater than a. Okay. And moreover, we also see that L is a linear operator. Okay. So what is the meaning of linear operator? You know. So L of f plus some constant times g is going to be plus c. Okay. So what is this operator is from? F is L is actually an operator taking f to say big Fs, which is L of f at s. So this is what we are writing it as f going to small f going to big F. So this is the transformation. And so for other functions with not going to converge functions, not even for all the continuous functions. Okay. So there are some, here you have seen that it's not defined for all s, it is defined only for s greater than a. Right. So let us use this linearity to find some more examples and to see how this Laplace transform look like. So there there are functions which are called cos hyperbolic functions and also sine hyperbolic functions. So this is basically cos hyperbolic at is nothing but half of exponential of at plus exponential of minus at. And now we can use the linearity of f to say that, to find what is this okay. So this write what is the, is going to be s minus a plus this is going to be s plus a. So this turns out to be s by s square minus a square. Similarly, you can write what is the of sine hyperbolic at by just sine hyperbolic at is e power at minus 1 minus e power minus at. So this is going to be a by s square minus a square. So these things have to be meaningful. So it's only true for s greater than a for the convergence of the integral. Similarly, you also have, you can write for the ft is sine at, okay, or the cos at, okay, and cosine of it. So we know from our complex numbers, we know how we write exponential of iota omega t. Okay. This is nothing but cos omega t plus iota sine omega t, right, where I is square root of minus 1. So, and we know the exponential of I omega t, so this is s minus iw. So by conjugating this, we can write this as s square by s square plus w square plus I times omega by s square plus w square. So writing the, comparing the real and imaginary parts using the linearity again, by linearity we get cos omega t as s by s square plus omega square and sine omega t omega by s square plus omega square. Okay, so these are some of the basic functions that we use in differential equations. So let's see how, let me, you have some, when you're solving a differential equation with constant coefficients, you have either exponential function or trigonometric function or hyperbolic functions, or multiplication of e power at into cos pt kind of functions. Okay, so what is the t power at into cos pt? What is the Laplace transform of that? So this is called the first shifting theorem, or the shift in the s variable. Shifting in s variable. What it says is, if L of f equals to big Fs, then f at s minus a is going to be L of e power at into ft. That is, if I give a shift of by a in the s variable, that actually amounts to multiplying the small function f by e power at. Okay, by e power at. a is a scalar. So the proof is not difficult, it's an easy proof. Proof is very easy. So you write what is f of s minus a from the definition. So this is the L of f at s minus a. So that is going to be e0 to infinity exponential of minus of s replaced by s minus a to t ft dt. Okay, so this is nothing but 0 to t into e power at into ft. So this is nothing but L of e power at into f. Okay, so this gives us what is the transform of Laplace transform of e power at into cos omega t. So this is going to be s minus a by s minus a whole square plus delta square omega square. So that is the shift by a. Similarly, you have e power at sin omega t. This is going to be s minus a whole square plus omega square. Okay, so similarly, one can use the integration by parts to show that Laplace transform of t power n is going to be factorial n by s power n plus 1. And also if I take any t power a, where a is a positive real number, you get this as gamma of a plus 1 by s power a plus 1, where a is positive real number. Okay, so this is how we see that for basic functions, for simple exponential trigonometric functions, the Laplace transform looks like. So the first thing is to look at generally how do we say that the Laplace transform exists for some function. Okay, so existence theorem. Existence theorem. Suppose f is piecewise continuous at on every finite interval of 0 infinity, and it satisfies the condition, which is these functions are known as exponential growth functions. Okay, for all t greater than or equals to 0, and for some k positive. No? So then the Laplace transform of f exists for all s greater than k. For all s greater than k. So these are the functions which are of the exponential growth at infinity. Okay, the functions which are having exponential growth at infinity. So these functions are all these functions will have the Laplace transform for s greater than k. Okay, so what are the functions which doesn't satisfy this is the functions like exponential of t square, exponential of t cube. These are the functions which doesn't satisfy this, because this is only of exponential growth. It cannot be of exponential of t square kind of. So the proof of this is we write L of f, okay, and we have to show that this is well defined. Okay, e power minus st. So this is going to be less than or equals to mod e power minus st into mod ft dt. Okay, so t is greater than or equals to 0, and anyway we are taking s is greater than k, and k is non-negative. Therefore, this is less than or equals to mod ft, and f is also having a growth of e power kt. Okay. No, you don't have to remove this, so keep this one as it is, e power minus st. Yeah. Okay, so this is you can see that this is nothing but m by s minus k for s greater than k. So that's what we said, that for s greater than k, this is well defined. Again, this theorem is only a sufficient condition. It is not a necessary condition. Okay, so we have seen already the one example I said you compute it. That is the Laplace transform of t power a. Okay, Laplace transform of t power a. So I said a greater than 0. So in fact, you can write for a equals to minus 1 by 2. Okay, so you can compute this. So this is only sufficient, not necessary. Okay, so for example, ft, which is equals to 1 by root t. So which is not defined at t equals to 0, and it doesn't have the, it doesn't satisfy the condition like the condition of exponential growth, I said. Okay, it cannot be controlled by exponential at t equals to 0. But you can check that L of f is going to be 1 by root s into gamma of. Okay. So that's how we define the Laplace transform and Laplace transform of some functions. So when it comes to the differential equations, the idea of the Laplace transform is that you transform the derivatives into some kind of an algebraic equation, because the algebraic equations are easy to solve. So that's what any transformation does. Even the Fourier series, that's what we said, that it transforms the derivatives into constant multiples through eigenfunctions. So here we are transforming, we are aiming to transform the derivatives into constant multiples. So what is the next theorem here is, if and f prime has exponential growth, then you can say that L of f prime is equals to f minus small f at 0. Okay, so assume that all sides f and f prime has exponential growth. Okay, has exponential growth, or Laplace transform of f and f prime both exists. Okay, then this is true. So even the proof of this is not difficult. So write what is L of f prime. So from the definition, this is 0 to infinity e power minus st f prime t dt. So apply the integration by parts. So when I apply the integration by parts on this, I get ft into e power minus st 0 to infinity minus ft into e power minus st. So we know that f is having exponential growth, therefore this is going to be 0 at infinity. Therefore you have this f is minus f at 0. This is going to be plus s into L of f. So that is the formula. So this can be used for writing what is L of f double prime. So for solving a second order equation. Okay, so this is going to be s into L of f prime minus f prime 0 at first step, and again apply the same thing, get s into L of f minus f prime 0 minus f0, okay, minus f prime 0. So that turns out to be s square into L of f minus s into f0 minus f prime 0. So you have a formula which transforms the derivatives of the function f into the multiplication by a polynomial. Okay. So these are some of the things that we can use for solving some transformations, finding some transformations easily, and also use it for solving differential equations. So let us see how it is going to be useful. So the Laplace transform of sine square t. Of course, we can write for these functions. We can also write directly the integral and then evaluate using the integration by parts. But we can use this formula also. Okay. So f is going to be sine square t. Okay. Then f at 0 is 0. And find what is f prime. It is going to be 2 sine t into cos t. Again, f at 0 is 0. And this is nothing but sine 2t. So f double prime is going to be 2 cos 2t. So apply our formula. You have L of okay, f double prime equal to s square into L of f, because f prime and f prime at 0 and f at 0 are 0. Okay. So if I take L of therefore L of sine square t is going to be 1 by s square into L of f double prime. So that is going to be 2 by s square into L of sine cos 2t. Okay, L of cos 2t. So, and we know what is the cos 2t, that is s square by s square plus s square minus w square, right? S square plus w square, right? So w square is nothing but 4 here. So this is how we can easily find, cancel those one s, therefore this is going to be 2 by s into s square plus 4. So the here given a function f, okay, given a function f, we are able to find what is the fs. But for the Laplace inverse transform, that is given inverse transform, given fs, can we find f? Can we find small f? Okay, so it's not always you have a formula for this. Okay, so you don't have a explicit formula like the formula that we have for finding the transform. So the way to write it is that if f is okay, if fs is the Laplace transform of f, then the inverse Laplace transform of big F is nothing but small ft. So this is the way to write the inverse Laplace transform. So to find the inverse Laplace transform of something, then you need to know for which function this is the transform. Okay, so that is why these things are, these kind of techniques for finding the Laplace transform will help us. Of course, there is a formula which uses the complex analysis, so which I'm not going to do it here. When you do the complex analysis course, then you will see that there is actually a formula for inverse Laplace transform of a function, but it requires some complex analysis. Okay, so for us, let us look at a second order differential equation. How this is going to be helpful for a differential equation. So how the second order differential equation looks like: an initial value problem, y double prime plus a into y prime plus by equals to say rt, with the y at 0 is say k naught and y prime at 0 is say k1. Okay, so take the Laplace transform on the equation. Okay, so assume that a and b are constants. So we have the L of y double prime plus a into ly prime plus b into ly equals to lr. Okay, so this we will write y double prime, I know, s square into, right, Laplace transform of y minus y prime 0, right, minus y prime 0 minus s into y at 0 minus y prime 0 plus a into s into Laplace transform of y minus y at 0, okay, minus y at 0 plus b into Laplace transform of y, which is equals to say rs, which is the Laplace transform of small r. So you can write the terms s square plus as plus b into Laplace transform of y is going to be rs. Okay, so you have the y0 equals to k naught, y prime 0 equals to k1. Okay, so rs plus s into y0, that is k naught, plus again y0, so again one more k naught, and y prime 0 is plus k1. Plus y prime 0 is k1. Okay, so this is what we have. So therefore Laplace transform of y, you can write it to be in the form of this upon s square plus as plus b. So the solution of this equation is to find the inverse Laplace transform of this function. So let's look at it's generally it is not possible for find, there are some assumptions where it exists and it doesn't exist, but for some equations we can always find the Laplace inverse transform. So an example, we take y double prime minus y equals to t, y at 0 is 1 and y prime 0 is 1. Okay, so by taking the Laplace transform, I get s square into, this is big Y, minus s into small y at 0 minus y prime at 0 minus big Y equals to 1 by s square. Okay, so this is nothing but s square minus 1 into big Y equals to, just substitute these conditions, I'm going to get s plus 1 plus 1 by s square. Therefore, big Y equals to s plus 1 by s square minus 1, that is going to be 1 by s minus 1, s square into s square minus 1. So this is going to be 1 by s minus 1 plus 1 by s square minus 1 by s square minus 1. Right, so now opposite this minus. And we know from the simple functions what are the, therefore the L inverse of this y, which is going to be my solution yt. You know that 1 by s minus 1 is Laplace transform of e power t. And similarly, 1 by s square minus 1 is Laplace transform of sine hyperbolic t. And last one, 1 by s square is a transform of t. Therefore, this forms now a solution. This forms now solution. So we identify the functions for which this is the Laplace transform. So from that we write what is the solution of this equation. So the whole idea is that this Laplace transform transforms the differential equation into an algebraic equation. And that algebraic function can be split into some small pieces like this, what we are doing here. And each of the small piece you can find what is the Laplace transform, inverse Laplace transform, and then write what the function is going to be. Okay, so like this there are other applications which we can use. So I will stop today's lecture here. So if you have any questions, you can ask me. Otherwise, I will stop it here and then continue tomorrow's class. I will finish the Laplace transforms tomorrow. Just have to do a little more things. It's anyways a small technique for solving initial value problems. Because this method, you will see that it's not just for the constant coefficients. I will also introduce some other formulas which will allow us to use this method for the equations with even variable coefficients. Some nice variable coefficients, not all, some nice variable coefficients. So sometimes it gives a nice method for solving the linear differential equations. Okay, if you have any questions, you can ask me. Otherwise, I will stop it here.
So Frobenius method थोड़ा सा elaborate कर दीजिए.
What?
Frobenius method, eigenvalues method, regular eigenvalue problem.
Regular eigenvalue problem. Okay. What is Frobenius method there?
So Fourier series method.
Series method.
Yes, sir.
Frobenius method. You didn't understand. There are three cases, right? One case. See, there are three cases. The case one is when R1 is, there are distinct roots. R1 is not equals to R2. And moreover, this R2, whatever you write, so if I write R1 is less than R2, okay, R1 plus R2 is not equals to R1 plus some number. Okay, it's not equals to for all natural numbers. In this case, you have two solutions, okay, which you can write using the recurrence relation. Okay, so the recurrence relation gives the solutions. And second, case 2 is when R1 equals to R2. So the roots are the same. So in this case, you will write one solution as x power R1 or t power R1, that's what we are using, times ck into t power k. Substitute in the equation and you will get the solution. Okay, substitute. That's what you will get, the recurrence relation, and then you will. And for the second solution, you definitely will have log t. Log t, okay, times the first function solution, plus you take an equation like this, ck t power k plus r, k plus r1, and then substitute this. Substitute to get solution. Second solution in the form of this. So this is how you get the two solutions. And third case is again in two parts. That is when R1 is not equals to R2 and R1 is less than R2, R2 is equals to R1 plus say some M0. Okay, M0 is some natural number. In this case, it is possible that you may find all the coefficients, okay, or it may not be possible to find all coefficients using the recurrence relation. So from the recurrence relation, you have a problem of finding the M0, this one, R2. R2 is going to be R1 plus M0. Okay, for some M0 means that R2 is also a natural number. Right, so R2 is a natural number and R2 is a natural number. Is a natural number. So it's the same thing in the here also. Yeah, R1 minus R2 is not this. Okay, right. So it's basically that you get something like I don't remember, PR into C k plus R probably is equals to something like TKR or something like that. Okay, so from this whether you can determine all coefficients or not. So you can determine all coefficients provided you have the P of R2 and P of R1 is non-zero. Okay, so in this case, if DKR is 0, so you may still be able to find the solutions. Okay, so still possible. Okay, to find all solutions, to find all coefficients, provided the right hand side is also 0 for M. 0 when P of R2, right? When you write P of R2, I don't remember this, TK of maybe. Okay, so if this right hand side is also 0, okay, when I take this as R2, then you can still find all solutions. So the other case is when there is a fourth case where you don't have such a situation, okay, where you cannot determine all the coefficients from the recurrence relation. That is, all coefficients, okay, cannot be determined from recurrence relation. So this is the case where you can do this. You can do, that is, can find all coefficients from recurrence relations. Okay, from recurrence relations, despite that P of R2 is 0. Right, so in this case, what you will do is there are two ways to do. First, write one's function. Okay, so both will lead to the same solution. There are two approaches. One approach is find the first function, find phi1, and second solution can be used using a formula. Second solution, you can write phi2 as phi1 t times a function vt, and find v2 and find vt. So this is a method. You know that for second order linear equations, if you know one solution, you can find the second linearly independent solution. And another approach is that you can write V2 as C times log t times V1 plus ck t power k plus r, and then substitute this in the equation and equate the coefficients. And we know that whatever the approach you use, you will get the same solution, because you know that second order differential equation, linear differential equation, has only two linearly independent solutions. Therefore, either of these approaches should give the same thing. Because it's an infinite series, we don't expect to know all the coefficients. So in this extreme case, we know that if we can have a method to find all coefficients, and if you can find first few coefficients, say first 3 or 4 coefficients without any difficulty, then you know that you can find all coefficients without any difficulty using the recurrence relations that you get. The only stark difference is that here there will be C. It's possible that C can be 0, because this method should work even when, in the previous case, when you are able to find the coefficients from the recurrence relations. Okay, so there also you can apply this, the second solution. There also you can apply this, also you can apply this. Both methods can apply in that case also. In that case, C will become 0.
Yes, sir.
Any other questions?
No.
Okay, so if you have no questions, let me stop it here. Tomorrow